this video we look at some matrix inverses. So one thing to think about when it relates to matrix inverses is, well, think of it like this. If I take A and I multiply it by 1, I know that I'm going to get A. Okay, that much is clear. But let's say, like, for instance, if I multiply by 1 on this side, I still get A. Okay, well, that's nice. But what if I was to take a matrix A, multiply it by another matrix, call it I, and have it give me A, and then similarly multiply on the left, and then it gives me the exact same thing. Now, one example that we can look at of these identity matrices is, for instance, like the I2 matrix, which is just really a set of zeros and ones, so you have 1, 0, 0, 1. So this would be I2. Another would be I3, which is basically the square matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. But then we can actually just generalize this to another matrix that we just call I sub n. So this is like the nth identity matrix. So like 1, 0 followed by a bunch of zeros, 0, 1 followed by a bunch of zeros, and then we have that this would be 1, not 1, but 0. And let's see, and then we'd have to have that this is a 1, and then we have to have that that's also a 1, and then we could put like a 0 here too, and then basically we have that that just keeps going. And we could put a 0 right there and a 0 right there. That way you kind of know that there's just ones in the diagonals and then zeros on the other. Now, how this relates basically is that, for instance, if I wanted to, say for example, solve a system where I have that, let's say you have the following matrix. You have 2, 7, 1, 4 multiplied by the matrix x, y, z, and w. Now this is equal to, let's say that this equals I2, so 1, 0, 0, 1. Okay, well that's telling you that, yeah, that you could have this unknown matrix right here. We can call this A, and then what we're going to call this matrix is A but with a negative 1. That means A inverse. Now notice that this is going to be equal to I2. Now maybe, I don't know, we can think of it like we're trying to solve for a systems of equations, because notice that if we multiply these two, that gives us 1. If we multiply these two with this one, that gives us 0. So it's almost like we're trying to solve a system. So in that case, we can actually do this very easily. Now, most likely, you've kind of learned already like the Gauss-Jordan method. So like, for example, we have 2, 1, 7, 4, and then we have 1, 0, 0, 1. Now, if I try to reduce this in a way that we can have the identity matrix be on this side, then that means that we have our solution. Okay, so if that's the case, then that means that we can just say, okay, well, how about this? We'll do 2 times row 2 minus row 1 to give us a new row 2. So that's going to give us, let's see, okay, so that's going to give us the following matrix. That's going to give us 2, 7. Okay, well 2 minus 2 is 0. 2 times 4 is 8 minus the 7 is 1. And then we have that this is going to be 1, 0, and negative 1. And then we have that that's going to be a 2. Okay, so it looks like here everything looks fine so far. So, okay, now our next goal will be to get this to be a 0. So let's say that we have minus 7. So we'll do the new operation. We'll do row 1 minus 7 times row 2 to give us a new row 1. So in this case, what that's going to do is it's going to give us the following. It's going to give us 0, 1, negative 1, 2, and then it's going to give us 2, but then that's going to give us a 0, then that's going to give us a 8. Wait a second. Minus 7, so that's positive 7. And there should be 6. Right, so if we multiply by minus 7, that's going to give us a positive 7, so that's actually going to be an 8. Okay, so that's going to be an 8. And then we have that that's going to give us, let's see, you have minus 14, so that's going to be minus 14. Okay, so next, all that we need to do here is just take 1/2 and multiply by row 1, and that's going to give us a new row 1. So what that does is it tells us that we have 1, 0, 0, 1, and that gives us, let's see, that gives us 8, well not 8, 4, negative 7, and then negative 1, and then 2. So notice that basically this told us that we have the I2, but now we have the matrix that we were looking for, which we call A inverse, or the inverse of A. So in that case, that means that the matrix A inverse, which was defined as the following, x, y, z, and w, is equal to the matrix 4, negative 1, negative 7, and 2. So just to kind of recap, what happened was that we took the matrix A, we're going to multiply it by A inverse, and it's going to give us the I2. If we do the same thing, like if we do A inverse equals to, not A inverse, but A inverse times the A matrix on the left side, it's still going to give us I2. So the whole point of this is that we can actually just augment and be done with it. Now, the whole process actually may seem a little complicated, that yeah, you got to perform these operations. And really, to be honest, the whole point of matrix inverses is if we already have the inverse, then we can solve for the solutions. Because if you would have, for instance, looked at the original question had that you were taking a matrix 2, 7, 1, 4, multiplied by x, y, z, w equals to 1, 0, 0, 1. Remember how I was saying that basically this created systems of equations? It creates the equation 2x plus 7z equals to 1. Then we have 1, or x plus 4z is equal to 0. Now that's basically one system. But if we do the same thing, we have 2x, 2y plus 7w is equal to 0, and then you have y plus 4w is equal to 1. So it's like we're solving for two systems of equations. So that's why we needed to augment this matrix to this matrix right here, and this matrix to this matrix right here. So it's a lot easier just to really just do it like so, where we go ahead and we augment it to just the matrix I2. So essentially, what we're saying is that all that you need to do is essentially just kind of switch things around where we'll say that, okay, so let's try to bring this together. So what we're saying is that one of the first steps that you would do is that you would take the matrix A and you would augment it to its corresponding identity matrix. The second step is that you would row reduce. Now, after doing that, then you would have that the solution would be that the augmented matrix has that now the inverse of that matrix A will now appear on the left side. Okay, but there is some possibilities. It is possible that A inverse might not exist. And that's where we get into some trouble. Like if A inverse does not exist, one example of when A inverse may not exist is the following. Like let's say for example that you have a matrix A and it's equal to 2, 4, 1, 2. Well, by that logic, you would basically find that you take 2, 4, 1, 2, you would augment it to 1, 0, 0, 1, and then you would probably tell yourself that you're going to take 2 times row 2 minus row 1 to give you a new row 2. But what does that give you? Well, it gives you the following. It gives you 2, 4, 1, 0, but then it gives you 0, 0, and then it gives you negative 1, and then a 2. So what this tells me is that A inverse does not exist. But that doesn't necessarily mean that, if we were going to solve a system of equations, that it wouldn't exist. So your question, or maybe right now you're probably wondering, well, if that's the case, then why am I even doing this? And again, it's only if we knew what the matrix was. So let me try to tell you that, okay, well, if we have a matrix, call it A, and then we have another matrix, call it X, and this is equal to B. Well, if we were to multiply by the matrix inverse, if it exists on both sides of the equation, well, that would mean that this would be equal to I multiplied by X equals to A inverse of B. But now, notice that basically this tells us that we have that X is equal to A inverse of B. So that means that the solution to any systems of equations is basically just going to be A inverse times B. Okay, but how can we put that together in an example? Well, in an example, you could probably say, for example, that let's say that you have a coefficient matrix. Let's say that you have a coefficient matrix and you call it 3, 2. Well, let's just say it has the entries 3, 2, 4, and 3. And let's say that x is equal to the unknown variables x and y. But let's say that b is equal to 16 and 23. Okay, but in this case, it seems that it's going to be a little difficult to find the inverse of the matrix and then go ahead and say that, okay, well, we just need to multiply by 16 comma 23 or 1623. So let's actually use our calculator for this. Okay, so um, we'll just say that, if you want to find the inverse of the matrix, you can just by augmenting it. So in that case, one option is to do the 3, the 2, the 4, and the 3 to find the inverse of it. But that seems like it's a little bit of double duty because basically it's going to only give you the A inverse only to have to multiply by 16 comma 23. So that might take too long. Because note that, for example, if you go back to the original question, not the original question, but the original statement of A x equals to b, algebraically you might be tempted to say, well, let's just divide by a, so I get b divided by a, and basically you might say, well, that's still the same thing as a inverse, or a to the negative 1 times b. Technically this is not correct, but actually symbolically that's the way that the calculator kind of makes it look like, is that we can actually just multiply a inverse by taking a, raising it to the negative 1, and then multiplying by b. Let's actually do that. So we're going to go to second matrix, we're going to go to edit, we're going to call this 2, comma 2, or 2 by 2. So that's 3, and that's a 2. Oh, okay. 4, and then 3. Now, we have that we need to input the matrix, let's see, the small one, the 2 by 1. So that was 16 comma 23. Okay. Now, theoretically, all that we need to do is just take the matrix A, raise it to the negative 1, and then multiply it times the matrix that we found, or that we input as a 2 by 1. So we hit enter, and we get the ordered pair 2 comma 5. Now, interestingly enough, if we would have found the inverse first, it would have looked something like this. 3, negative 2, negative 4, and 3. So we basically kind of stated that the solution is x equals to, so we said that that's going to be 3, negative 2, negative 2, and then, or not negative 2, but negative 4, and 3. And this was multiplied by 1623, and this happened to equal to 2 and then 5, which means that basically the solution is the ordered pair 2 comma 5. Now you probably could have plugged this into, let's say for example, like a graphing calculator, and it would have gave you the exact same thing, which it's really all the same. So yeah, you could have done this, but really again, matrix inverses is only really if you have it and if it exists. Now, I can do like one more example of when we might use a matrix inverse method. So for example, let's say that a movie theater charges $8 a ticket for adults. But let's say that they charge $6 for seniors. Now, in any case, on a particular weekend, the attendance was 525 people. And then we have that the receipts, well, the receipts were said to be $3,580. So if we ask, for instance, how many seniors, then in this case, what we can do here is just set up our systems of equations. So if we set up our systems of equations, we know that basically x could be the number of adults and y could be the number of seniors. So that means that we can set up our system like x plus y equals to 525. Okay, so that takes care of this one. And then we have that the receipts, well, if we know that 2 adults attended, then that's $16. If we know that 1 senior attended, that's $6. So in that case, that's telling me that the cost is 8x plus 6y equal to 3,580. Now, what that tells me is that basically we can set up our systems of, or we can set up our matrices actually. So for instance, we know that we could say, like, for example, that A is the coefficient matrix 1, 1, 8, 6. Then we know that B could be the matrix 525 and 3,580. So that means that in this case, the vector, or the matrix x comma y, that's where your solution is going to be. So first we need to find basically the inverse of A. So we'll go ahead and go to second matrix and we'll go ahead and just edit the old one. So it was 1, 1, 8, and 6. Okay. Now actually let's go ahead and find the inverse of it. So the inverse of this matrix is the following. Now we might get some decimals, which in this case we can actually just go to mathfrak, and that's going to give us -3 1/2, 4, -1/2. Okay, so here we found that A inverse is equal to 3 -1/2, and then I believe it was -4, -4 1/2. Let's go ahead and check this out. Was it 2 negatives? Oh, okay, I think I got it backwards, yeah. Okay, so it's actually -3, and then it's -1/2, and that's a +4. Okay, so what we need to do here is just multiply the x, so, or just figure out what the x is. So x is equal to -3 1/2, and then 4 -1/2 multiplied by, well, in this case it's going to be multiplied by the attendance and the receipts. Okay, so let's go ahead and go back, and what we're going to do here is we're going to go ahead and just input the matrix that defines the attendance. So, oh, it's a 2 by 1, right? Yeah, so 2 by 1, so that's going to be 525, and then that's going to be 3,580. Okay, so that means that we can actually just do this all in one. So while I do know that, A inverse is the following matrix that we wrote down, I can still, compute it, multiply it by the matrix that I saved, and it's still going to give me the solution. So we have that the answer is 215 and 310. So that's going to give us 315 and 210. So we have that, okay, yikes, okay, I accidentally switched those on accident, so, okay, so that should be, it's 215, right? Yeah, 215 and 310. So in actuality, there were more seniors than adults. So in this case, like, we would say that there were 310 seniors that went to the movies. Okay, so that's one way that we can actually use inverse matrices, okay? Now, one thing that I can recommend to you is that if I have a matrix, call it A, and it's A, B, C, and D, interestingly enough, the inverse of that matrix is given by 1 divided by AD minus BC multiplied by D, negative B, negative C, and then A. So this is the formula for finding a inverse of a 2 by 2 matrix. Now, this is, however, provided that AD minus BC is not equal to 0. Otherwise, if it is, then that means that the inverse does not exist. So that means that basically that if A inverse does not exist, then that means that there's two possibilities. You either have that there's an inconsistent system, which means basically no solution, or that you have that there's a dependent system, which means that there's actually infinitely many. So that's kind of interesting that if the inverse doesn't exist, that you have that those are the possibilities. Now, I'm going to go ahead and just give you an example that you should try with regard to finding an inverse. Okay, so I want you to go ahead and try finding the inverse. So go ahead and try to find the inverse of A equals 2, 1, 0, 1, 2, negative 2, negative 1, and then 3, 0, 0. And try to use it, try to do it without using a calculator. But if you do use a calculator, then of course you're going to have to change it to fractions, so that way you kind of know what to do. To get you kind of started with, like how would you do this by hand, I would not recommend that you try to set it up with, entries X, Y, Z, and so on, and then try to figure out what each one is, because that's going to take forever. So just go ahead and follow the process where you have 1, 2, 3, 0, 0, negative 2, negative 1, 0, 1, and then you're going to augment it to 1, 0, 0, 0, 1, 0, 0, 0, 1. And then from there, you just perform the steps. Unfortunately, you're going to see that basically it's almost like it's n squared. So in this case, it'll be up to 9 steps. But if you compare it to the calculator, you'll see that, it is a little easier, but it's good to know kind of how to do it in that case. Okay, so if you do want to use the calculator, then yeah, you'll just end up going to the matrix and then just make sure that you do your entries 3 by 3 and so on. Okay, so really the inverse method will only be very useful if the inverse exists only. And sometimes we like to say the phrase if it's already available. So if it's already available, then in that case, by all means, use the inverse method. But if that's not available, then that means that, yeah, you'd have to go back to those other methods, which that's what I forgot to say, is that if the inverse does not exist, you would have to go back and you would have to use the other methods to find if it's a no solution or if it's infinitely many. Okay?